Usually following an astronaut presentation is really difficult because of the video and the pictures. I was really disappointed to not see Michael's video and pictures, but it makes it a little bit easier to follow an astronaut without that. Also, I always, I'm a NASA guy. I'm going on my 28th year at NASA and with the government, and so at these public meetings recently, I felt compelled to come up, and the first thing to say is, I'm from the government, I'm here to help. And hopefully you'll get an appreciation for why that is in my talk. We have this tagline at NASA that technology drives exploration, and we came up with this several years ago as if that was something new. Well, technology has always driven exploration at NASA and in general, and it's new. It's absolutely true today. I love the Tang and the Velcro as the two examples of technology from the Apollo era versus integrated circuits and like advanced materials, right? So, but the Tang and the Velcro thing, we just can't shake that. How many people here know what Tang is? That's a pretty good. I'm surprised that many people actually know what Tang. I know you know what Velcro is. So yeah, technology has driven exploration forever for the history of humankind, including space exploration. We are, because we're trying to do some really challenging things, right? So right now we're trying to extend human presence beyond low Earth orbit and enable human exploration of the solar system, and that's going to be very challenging, and lots of technologies and new capabilities required to do that. We're trying to enable the next generation of robotic missions for science, both for Earth science to continue studying the Earth, as well as to unlock the mysteries of the universe. I think there's just a couple of things that are really driving that robotic exploration now. One you saw, and that is exoplanets and finding planets around other stars. It's just incredible, including the TRAPPIST, the 7 planets for TRAPPIST system. What we haven't been able to do is do direct multispectral imaging of exoplanets. We believe we can detect water vapor, methane, carbon dioxide, and oxygen in an atmosphere of another planet. There's very highly likely life as we know it on that planet. And so we're developing technologies to do that. We're also developing technologies to, say, land on Europa and drill through the kilometers or melt through the kilometers of ice on Europa to the liquid ocean underneath. And we think that there may be life on ocean worlds like Europa, and we're going to search for that. So lots of tech to do that. But we're also trying to develop technologies. Well, we have multiple ways in which we support the commercial space enterprise in this country. And Michael alluded to several of those. The first thing that the government should do is provide a regulatory framework, a regulatory environment to remove barriers and encourage the development of commercial activities, including commercial space. That's not NASA's job. We're not a regulatory agency. It's the FAA and others, and administration and Congress that sets policy for civil space. But that's really important, right? We don't do that, but it is really important. The other thing we do is kind of create this initial demand. And Michael talked about commercial cargo and commercial crew, where the government paid money and created this initial demand for services, and that allowed companies the capital investment to then use those services in other sectors beyond NASA and beyond government. That's the other model. We're going to continue to do that, particularly in the human spaceflight world. And then there's technology development. Developing technologies to enable things that we could not do before, enable capabilities that we didn't have before. And some of the things we're trying to enable for the NASA mission are more efficient and rapid transportation through space, getting places more quickly and more efficiently. We're trying to enable landing on other planetary surfaces, heavier systems, larger systems with more precision in some really crazy terrains. Mars is really tough, but we're also looking at landing on some really interesting other planets, like planetary bodies like Europa and Titan. And then there's the technologies and systems that are required for human exploration. Michael mentioned environmental control and life support. We need to improve the performance and reliability of those systems above, as compared to what we have on station if we're going to push out beyond low Earth orbit. So there's some examples of things that we're creating for the NASA mission. It's also important, I think, business model innovation, the way we go about doing these things. We always like to talk about the technology. We're scientists and engineers and talk about the cool tech, but also business model innovation is really important. And so we're still doing grants and contracts with universities and companies, and spin-offs and tech transfer. But we're also in the last few years also engaged in things like public-private partnerships more, crowdsourcing, and prize-based challenges. Just different and more unique ways of both getting technology developed as well as having a larger set of contributors to technology and the really tough things that we're trying to do. Because what we're trying to do, it's not just government, it's not just universities, it's not just commercial, it's not just US, it's international. It's kind of all hands on deck. Because we're trying to do some things that are really hard, that are going to take a lot of talent and a lot of resources to do. So we've also kind of looked at different business models and different ways of engaging a broader set of contributors to our program. And one of the areas where we pretty much used every one of those models is advanced manufacturing and in-space manufacturing. Now, like any innovation, there are several technological advances that are made, significant advances in terrestrial manufacturing, but also enable in-space manufacturing. Obviously, one of those is 3D printing. I mean, 3D printing has really revolutionized not only the way we manufacture things, but the way we engineer things. The advances in 3D printing are not made through building a current design using 3D printing manufacturing. It's ripping that design up, taking a clean sheet, and looking at what 3D can do from a design standpoint. And you actually can come up with some really interesting designs that you now can manufacture using 3D printing that you can build that you couldn't before. And so I can't underemphasize the importance of that technology. There are others to go with that, like a lot of innovations, to the integration of technologies together to deliver value, a new value to a customer. The other is advanced materials. We continue to advance materials, and that moves manufacturing along. For space, autonomy is really important. Highly autonomous, reliable systems is going to be really important for robotic in-space manufacturing. And then for space, one of the biggest barriers, if not the biggest barrier, is low-cost access to and from space. Right? We talked about being able to, we would have to be able to, in a low-cost way, launch the infrastructure to space, launch the materials to manufacture things in space, and get finished products back down, like Michael alluded to, when we'll manufacture things, say, on the International Space Station. So those are all really important advances which are now enabling us to think about in-space manufacturing and assembly type of systems. So we've got several activities ongoing within the agency to advance this area. One is on the space station, and one set of activities on the space station is just that, to manufacture things on station in the space environment, particularly the microgravity environment, to manufacture things you can't on the ground, or manufacture things with higher quality than you could on the ground, and bring them down to Earth for terrestrial uses. And things like pharmaceuticals and materials, fiber optics, et cetera. And so that's something we have been doing on the space station, we'll continue to do on the space station through hopefully at least 2024. And then we are hoping there are commercial space stations in low Earth orbit that will continue this opportunity to manufacture and bring things back to Earth, as well as available to NASA to do research after the ISS era. The second area is related to the logistical burden of deep space human exploration. I don't think we can bring all the spare parts we're going to need for all the systems to, say, do a human mission to Mars. And so using 3D printing technology to be able to send or have a software catalog on board to be able to print supplies and print spare parts is going to be really critical. And in 2014, a company called Made in Space launched the first 3D printer of the space station and manufactured some plastic parts, and we brought them back, and it turns out that the properties of those parts manufactured in 0G are just about the same as parts manufactured in 1G. So that's good. That's good. We know that it's viable, at least for that technology, to manufacture things in the low-gravity environment and have them be useful to crew. And then the third thing we're developing are technologies and systems to do in-space robotic manufacturing and assembly of entire systems and spacecraft using 3D printing, robotics. One thing I forgot about that's a big technological drive in this area is robotics also. To use 3D printing and robotics to manufacture and assemble entire systems and spacecraft in space. When you think about it, so much of the design constraints of a spacecraft are driven by the 7 or so minutes to escape the gravity well and the launch environment. We're thinking about the loads and dynamics of that environment, and it really constrains the system design and drives costs. If we had a manufacturing capability in space, we could launch feedstock in that environment, which would be pretty easy to do, and then optimize the spacecraft design for what's a relatively benign, mechanical environment of space and manufacture and assemble. We have 3 projects. One is with Made in Space, one is with Autolave DK, and the other one is with Space Systems Around. They're public-private partnerships. All those companies are putting at least 25% of the funding to do these projects with. They're going to start with a ground demonstration of 3D printing and robotically assembling systems, and then hopefully we'll get to a spaceflight demonstration of a structural system, like kind of to manufacture and assemble in space the backbone of a spacecraft. And so that's what we're aiming to do there. A couple of other things, we've used challenges. We have a challenge now called the 3D Printed Habitat Challenge. And it's to use a little bit of water, a little bit of power, 3D printing, either soil or regolith, lunar or Martian regolith, and inorganic trash, plastics, to print the components of a structure that could be assembled into a habitat, say on the surface of Mars. We had over 80 organizations put in their intent to participate in the challenge, and I think about a little less than half of those are from foreign countries. So it's good. I can't wait to see what comes out of that. It's sponsored by Bechtel and Caterpillar, a large equipment manufacturer, and run by Bradley University. So we're really excited about that challenge. It's focused on kind of living off the land, using local resources to manufacture structures. And the other thing, we just awarded one of our first space technology research institutes. The lead organization is Berkeley University, for biomanufacturing. Instead of using biological processes to produce materials, and then using things like 3D printing to actually use those materials to manufacture things. So that's even trying to lower the logistics burden even more by bringing the minimum amount of material and actually growing material and then printing. We're also, as part of that, looking at improving the process to grow food, to provide food for crew for long-duration missions. So that's a little bit about what's going on in manufacturing. Like I said, there's a ton of technology and new capabilities we're going to need to do the missions we want to do in the future, including for human exploration of the solar system, as well as the robotic missions. And it is all hands on deck. We need everybody to contribute and participate. Well, thank you for this opportunity. Thank you for your time.